Okay, so let's
Yes.
start. It's my pleasure to welcome one of our own organizers, Hong Van Le, from our institute in Prague, and she will talk about diffeological statistical models and diffeological Hausdorff measures. So please go ahead.
Okay. Thank you, Igor, because usually our seminar is more oriented on the traditional branch of mathematics, algebra, geometry, cohomology, physics. Yeah, but I think that static is actually is the new thing in this century. As a physics is coming to the mathematics. If I just let me remember that who is first mathematician, not first, I mean that's a great mathematician who interested in physics, that Hinberg. Hinberg says that physics something like too complicated for physicists. Of course, he joke, but that is why he tried to work on physics, and the statistics is related to artificial intelligence, machine learning, and I already advertised sometime on the Srini conference before us. There are already Mumford May working on this film. So that's they are film medalist in geometry. Yeah. So we are not kind of the pioneer, but I think it's still very exciting. Actually, I interested in such a thing when I talked to former PhD student of SMAI, and he told me there are a lot of interesting mathematical problem in this field. Okay, so plan of my talk is as follow. First, I should say about the diffeological space and diffeological statistical model. So the idea is to how to say you want to do mathematics, then you have to put mathematical structure. Yeah. And that mathematical for us differential geometry. I mean that's yeah must has a background differential geometry and apply algebraic method, topological method in physics. Then that is a differential calculus, and differential calculus is invented by Newton to solve problem in physics. And then I should explain how this idea of the differential calculus invented by Newton to solve problem physics, and then had been developed faster in many ways, kind of generalize a smooth structure, and the diffeological spaces is the one very convenient category to do um, uh, variation calculus and differential in calculus, yeah, and that's how to make it apply to statistical model. And actually, I should say that it's not completely that's first. Recently, you hear about information. Could be some people do it, but there are also many famous statisticians doing it, but they use a different language, and maybe therefore not so convenient. And I cannot translate the answers this language in statistician, but I should mention some of them. Yeah, and the sense what is the most important, because every time in units estimate unit metric, and the metric units that is a diffeological Fisher metric, and you also need measure and Hausdorff measure. And everything here is related to notion of smooth structure. And to explain that our construction is natural, and use some categorical construction in the statistics probability, and then using construction. So that is not completely, how to say, traditional statistical approach, but try to do some categorical, algebraical, geometrical. That is the aim of our seminar, yeah, to discuss completely new idea and apply to this field. And then the last part mentioned very briefly how to apply, why they are important in statistical physics and machine learning. Yeah, statistical physics is already Eivind Schneider discussed something about thermodynamics last year, and that's why he interested in coming. And of course, I should mention something. but that is very briefly because we are not on the course of the statistical physics. Okay, so his story is how to say difference is why you need the diffeological spaces, yeah, and the diffeological statistical model is adaptation of the notion of the diffeological spaces to statistical model. So that's the problem is motivated by physics and the geometry. Of course, I didn't mention here Leibniz. Leibniz has a more motivation from Feynman mathematics, but Newton is really motivated by problem physics, and he invent differential calculus. But differential calculus can be work even in the later part, 80 of the last century, work on only regular geometric spaces, which can be also called differentiable manifold. And then, with the development of physics, we know that many things singular happen in physics. For example, singular reduction of symplectic spaces, and many things more. Yeah, you can look at the book by Diffeology of the Patrick Iglesias Seymour, the best book on diffeology. He was a PhD student of Suryo, yeah, and Suryo invented in 1980 because of this problem, try to give unite and a relatively simple treatment of regular and new singular object in physics. Of course, it means that there are no universal theory for everything. Something very complicated, and you need to applies a more complicated theory, but diffeology is has a how to say relatively simple treatment of regular singular object and infinite dimensional. And the infinite dimensional is a many problem in statistical physics. As I mentioned briefly, we can also treat it a diffeology. Okay, so now is my definition. Adapted from the Iglesias Seymour. So let a little bit different, but that is there are many things open question. Yeah, so I shall discuss later. For case is integral up to infinity, and the x is a non-empty set. Then a CK diffeology on x is a set of the on mapping from the open domain on finite dimensional vector space to X suggests the following axiom hold. The covering, that means that we have to on the constant map. The locality is something that's like a sheet theory. Yeah? If you have the, you can glue together, then it belongs to the whole thing. Yeah. So that locality is that open map, so that P restrict to V belong to D, and map B belong to D. And then, so that it looked very like the usual theory of the differentiable map, but what you miss, and I should explain the smooth compatibility. That means that for every element from UX and real domain V, then CK mapping from V to U give to the composition, also the smooth mapping. So the difference from the theory of differentiable mapping that you done the smooth compatibility is weakened. You don't need to inverse transition map. You don't have transition map. You have only smooth compatibility. Yeah. So that's so that's a CK diffeological space, a non-empty set equipped is a CK diffeology. An element of the diffeology will be called CK map from U to X, and U is the only open subset of finite dimensional vector space. And that is the finite dimensional vector space is very easy to do, because once you go to infinite dimension, then the terrific thing. Yeah. So of course it's important, but sometimes you need only certain thing, like Einstein also say, yes, many things infinite dimensionally can be treated using this such kind of the diffeology theory. So now once you have a smooth compatibility, you can define that a map between two CK. Diffeological space is a CK map if for ADP in D you have composition in D prime. So that's exactly like a compatibility condition of D3 now extended. So that's a natural. So what is the difference from the original concept of the diffeology? Because in diffeology, they consider only C infinity map. Because the category of the C infinity diffeology is a convenient, in particular Cartesian closed. But on the pupil in category, that they just ignore the CK, that they ignore a lot of things. Yeah, because in analysis you have to use a lot of different space. So the theory of the CK diffeology, and there are many questions like that. Yeah, just could be problem thesis for many people working interested in extending the functional analysis to theory of diffeology. So that you don't have the, if you work on C infinity, you have Cartesian closed. If not, then not. So that is why people on the theory, they only consider smooth mapping and they ignore anything CK. Now, example, let we be Banach space. Then we have the canonical CK diffeology, and I denoted by DK. That consists of the how to say, CK differentiable mapping from U to V, because you know that's a CK mapping between the domain in Rn to Banach space, because the notion once you have Banach space, and the definition of CK mapping is a standard. Yeah, so the theory of Banach space, that's Lang already wrote in his book Fundamental Differential Geometry. Almost everything work for finite dimensional manifold, work for Banach space, except very few cases. Yeah, so that's why the Banach space very simple thing, and then with Banach manifold. But of course, that except very few things. But now you have something more. If you consider infinite dimensional, that is interesting. You have another diffeology that consists of on weakly CK differentiable mapping, and U is an open domain. So what means that's a weakly differentiable mapping? Because that's you know what it means, that's weakly convergence, right? Weakly convergence in infinite dimensional model, that means you take the composition with because you consider the dual space. Yeah, so on this functional, I will compose it functional on the dual space. Then of course, I mean dual space continuous, yeah, because space, then the map is convergence. So if the manifold Banach space is a finite dimensional, then two diffeology is the same. If not, they are different. Yeah, and there are more subtle between just weakly weakly star. Yeah, so that's you take the double of the dual space. So that's very popular in the measure theory. But I don't want to discuss so many different notions of the weakly or weakly star. But in this settings that I use the notion of equilibrical differential mapping. It's strangely only formulated by many people, only for case k equal 1 in many paper, but for any case only first time in the appendix book of our book information geometry. It's Nihat A. Jürgen and Lorenz Schwarzhofer. So this concept first completely for any k formulated in the appendix. Otherwise, it's only for k equal 1 in other paper. Now it defines the notion of pull-back diffeology, because everything is a categorical. I mean, that's a define, except that k is not equal infinity, you don't have Cartesian close. Yeah, so it defines the pull-back, because then function, you can take the pull-back, right? And the notion of function, that means that the diffeology is a set of the, not the how to say, the CK is F is 6 to X. Then pullback of D is on that U to X such composition of F to P is belong to D prime. So just rewriting some composition mapping, and you can have the push for R. That push for R, that means you have the map diffeology on X, and any map from X to X, and put the map, you call that the map U to X is a CK map if the AF to P belong to D. Is that correct? To D, I mean that's a push for to, I'm sorry, that doesn't mean that's a annotation. So that is I have to check my paper, our paper on. So that's a push for F D is on X, and here must be U to X. Yeah, suggests that is F to F equal F I have got X from the you have to U to X into prime X prime, then map from U to X is a smooth map. It's a composition of the map from U to X and the F here. So that means that's a P equal here that's a P here, F to P, yeah, F to P, and then P prime and P prime but equal P prime equal F to P. So I'm sorry, but if you write the diagram in category, you see immediately. But that course I give the lecture here, I should see that if I make some kind of the typo like that in some my paper. Okay, then I should erase. Okay, so then let it go further. Now, very good. So think now I go to the category of the statistical model. That is general theory of diffeological space. But so what is I have the diffeological statistical model. So look at the space of on finite sign measure on a measurable space X. It's a Banach space. It's a total variation norm. Yeah. So very good. And the definition of such a model is any subset in the set P. That means on probability measure on a measurable space X. Any. Yeah. And the set of the on.
Sorry. Sorry yes? to interrupt. Can you close the annotation menu because it obscures part of your slides.
Close the annotation menu. Yes, right.
Yeah.
Yeah, thanks.
Okay.
So now is a P of X is set of on probability measure, and S of the X is a sign measure, and the statistical model is any subset in probability measure. So I is important because from the last century, people on the day when claim that the main problem is to define of statistical science. Yeah, or they say that even statisticians, the main problem of science is understanding our phenomenon. How to say, what is the probability distribution of the phenomenon you observe? Yeah. So then, okay. So the thing is to understand this which probability distribution, that's like a mathematics. You cannot consider the set of on mathematics structure, then you do something, you cannot do anything. So you have to choose some kind of statistical model, set of you things as where probability measure of the phenomenon you are observed and that you want to define. And then, for example, people working in statistics, usually they consider only normal Gaussian distribution, but different parameter, yeah. But then later on, you say that you think that there are much more phenomena distribution, not only Gaussian, and then such kind of definition I took from the paper by Makula. Yes, a very famous statistician from University of Chicago. And then you can and many people of course, and you can consider that traditionally differentiable manifold or smooth, but now let us consider any statistical model, that means any subset in probability measure. Now I give the following definition of how to put the diffeological logic on any statistical model. I mean that's a statistical model, let it have some diffeology, and now icon is a diffeological statistical model equally diffeological statistical model if the E is an inclusion of Px to Sx, yeah, so that you consider Px is the inclusion on the Banach space of total variation norm. And Banach space very nice space, yeah, has natural smooth structure, right? Then that inclusion puts the of the dx is belong to canonical diffeology on Banach space or on the not canonical but equally canonical but equally diffeology, and you know that's a different, yeah. In my paper in 2002, I define only on the canonical, and later on is a Tuchelin. We consider also equally CK diffeology, and you show that's a yes, they are not. I show that the people in statistics already know that, but they use a different language and a different thing, so it try to make it very precise, general, and abstract, and blah blah blah. Yeah.
Sorry, Ivan, just to clarify, so this you're defining a diffeology on this curly X, and the curly X is the space of events?
Yes, curly PH is any subset in the of the probability measure. On the X is a measurement space. If the X is a sample space, that is a measurement space.
Yeah, X is a sample space, and the diffeology is defined on which space?
On the subset of the probability measure.
So on this PX that you have on the top.
Yeah, yeah.
Okay.
So a sectional model is a here
so
PX.
So the diffeology would be, so the diffeological space would be this tuple PX with a diffeology DX.
DX, yeah.
Okay. And what
PX is DX, yeah, CK.
Yeah.
It's, I mean, that's a first consider PX set and consider any abstract CK diffeology, yeah. And then I score that is a diffeologic or statistical diffeology, maybe that like that, but because it's a thing is a statistical model, otherwise it's better to call that a statistical diffeological space.
Okay.
But if I call that a statistical diffeological space, people in statistics maybe not so interested in.
Okay. No, but just to clarify, so this I mapping, what is this? The I?
Inclusion of the PX, the subset on PX.
Okay. So like on the top line, you have PX included in SX. That's the inclusion.
Yes,
that's little I. Okay. All right.
Yeah. So. So now example. Now example is a first. That's a very thin. Actually, how to say example? That means that for example, you consider in our book information geometry is the people. The notion of parameterized statistical model that M is smooth but not manifold because smooth bidimensional, almost like a finite dimensional manifold, except a few technical complication. And then you consider X is a sample space, P is a second map because I is an inclusion, yeah, P and to S6 to Banach space, you know how to define CK map, yeah. So that is but that is everything is parameterized because you need some map P from M to space of on parameterization in the almost on the time on statistics they consider only parametric, yeah, they call the parametric, sometimes they call parametric because they can only consider finite dimensional, so non-parametric is a infinite dimensional, but that is why we use a not parametric completely parameterized, but the thing is idea is how to say parameterization is like a covering resolution of singularity and algebraic geometry. Yeah, you have some base set, you have the set of parameter is nice set, you put covering, yeah, on the base set, and understand you do everything on the covering space is a nice thing, and therefore you can know something on the image of it. Yeah, that is the idea of the parameterized on the parametric statistical model. And the diffeology is says that you don't need such kind of covering or parameterization. And then how to say the image of the by definition PN is subset of the probability measure, and the push forward of the decay canonical diffeology because the N is a Banach space, it has a canonical diffeology, and then this is a CK diffeological statistical model. And there are more many things interesting now, but before to say some interesting thing, I say about the geometry of it, and the first approximation is a tangent cone. Yeah, so the tangent cone is a definition very naturally because once you have curve and assuming it's a CK map because you define as a CK map, then tangent vector is an image of DCT in SX because everything, how to say, everything is a go from the X to Banach space, and the SX is the only subset on it. Yeah, so the image of it, and this is a C naught is a weak differential because if the you consider the is a that weakly Seka differentiable or the Seka differentiable, but we know that every differentiable map is a weakly differentiable map, and therefore I decide from the today talk that I should remove weak because it's it agree is the concept of tangential vector in theory diffeological spaces. In the theory of diffeological spaces, they then consider the mapping to Banach space where you have the different diffeologies, therefore there are no notion of the tangent space differentials, and then the notion of differential and tangent space only came and you consider Banach space or anything kind of infinite dimensional. Yeah, and therefore I decide that from today and in later paper I should remove it because that is clear from the context that if the compatible is a diffeology on the diffeology on the Banach space, and it's a big differential. Yeah, so that's now I say the only tangent cone, not anymore tangent cone. Yeah. So tangent cone, the concept I forgot here should remove the VW that for it. Tangent cone, it consists of the on tangent vector. Yeah, because it already they know the notion of the tangent vector, and tangent space linear horn of tangent cone. And then why is it interesting? Using only such kind of first geometric approximation like a tangent cone, you can distinguish different C1 diffeology on a given statistical model. Yeah, so that's when I asked Patrick Iglesias Semua if he has a different example of different diffeology on the same subset, somehow compatible is another thing. He says that, oh no, but he is very busy teaching now many course on Zoom for student in China. But then that's if you look at our paper, you see that you have the examples of the different no, not only diffeology, statistical given statistical model that means compatible with diffeology on the Banach space. Okay, so that's a first idea of the diffeology, and why it's applied to statistical model is very natural, because it already have natural smooth structures here. And if I have time, I should mention that some statistician before had considered something like that, but maybe already in my example here. Now we consider a diffeological Fisher metric and diffeological Hausdorff measure. Now consider that a CK diffeological static model will be considered almost to integrable if the I forgot to say what is logs of the tangent vector. I'm sorry, that's the one of the lemma annotation. I forget to write here, but in our paper that means that if the V is a tangent vector in T, that means cone of C of the Px, then V is dominated by C. That's a very important lemma. That's dominated by Radon-Nikodym theorem. Then it has a dV dC is a function in L1 of the xc. That's a very important theorem. Yep, that is written in the. Of course, that's a many cases. You can see the a little bit history in our paper is sometime I write 2020, sometime 2021, because it put in November last year, but the second version is planned to put in this March. There are many typo and in that paper, but generally that's I think that's a no serious mistake. So I should erase it. So and then this Nikodym derivative of the dv and the c equals that logarithmic tangent derivative, because that's a function. So that's what's interesting. From the measure you go to function, and the function is surely just simpler than measure. So now I would say that on people before they consider only density because the density function, but actually you have to consider measure and not density, because the density is a covariant object. You go back to not how to say, and you have mappings that the covariant and measure is a contravariant, go it's the other way. So if you identify function with the probability measure, you may confuse. Yeah. So that's now I consider the tangent tangent vector, that is the probability measure, but thanks to Radon-Nikodym theorem, I take the log of it, that is a function, and the function I say that it Radon-Nikodym theorem says that it's only in L1, but now I assume that is L2. It is L2, then I call that a diffeological statistical models are almost to integrable. And once it's in L2, you can define the diffeological Fisher metric by V and V at the log of V is the Radon-Nikodym derivative, yes, that function, and the both and L2, then you can take the product of them and integrate, yeah, and that is exactly Fisher metric. Diffeological because it define on anything, it's only this condition. And once you define on cone, it extends naturally to a positive quadratic form on tangent space, and we also call as a Fisher metric. And then it's called as a two integrable. If you need some continuity, that is important for, yes, function must be continued to have the many interesting property. Yeah? So what is the continuity? ADV here, you take the norm of this or length of the V is continued on space of TU. TU is only open domain in R, and TU is kind of actually such a product space on the R2 and everything is had natural topology. So let PX be two integrable CK diffeological model. Then you can define the CK curve. Now first I expand from the open interval to closed interval. If I can extend a bit interval faster, and then I say that there is a smooth map and restriction to that interval is a C. Yeah, so that's how to define the CK map from the closed interval by like the differential geometry, it makes some polar neighborhood. Yeah, and once you have the notion of the on the interval, you can define that. It means that piecewise CK curve. If the finite number success, that the restriction on each interval is CK curve for each closed interval. And then you can define the length of the piecewise curve like that. Integration of C on like in Riemann geometry. Also for the piecewise CK curve as a sum of the length of CK smooth subinterval. Yeah. Now I define the diffeological Fisher distance between 2 points as the infimum of the length over space of piecewise CK curve connecting X and Y. And if there are no such a CK path, then you put it at equal infinity. And the improved theorem that distance function is extended matrix. That means that normal a matrix, if it's not equal infinity, satisfies the triangle inequality. Yeah. So that is why such interesting, because when people consider parameterization, they only have to show that yes, that is that one-to-one or something like that to make the Fisher matrix non-degenerated. But the define in this way is it only non-degenerated, and once it's non-degenerated, you can define the notion of length. Yeah. So we already quotient out on this degeneracy by going directly to the subset of the probability measure. Now
Can
go
I
to
ask?
the
So
yes.
if you use C0 curves to define this metric, do you just continuous curves instead of CK curves? Do you get a different metric, or it's the same metric?
Oh no, that's I need the C1 because I take the differential here.
Ah, yes, yeah, okay. Okay, but if you change K from 1 to 2 or 3, or that doesn't really change.
Yeah, so that's how to say. On the people working on the diffeology, they avoid the problem of CK, and I think that's there are many things I don't understand. Yeah.
But here, I think this has more to do with the properties of the Fisher metric.
Fisher metric, yes, of course, you can prove some inequality. And then, but I say that's going from CK to the different, how to change from C1 to C2, and what is the relation of them. Nobody do it, so you can keep the problem for first master,
Okay.
bachelor, or PhD.
No, nobody checked. Okay, all right, thanks.
Yeah. So that's a completely, how to say, because the people working with the C infinity, they take category and close every consonant. But actually, that main thing problem in PD use oblique by using kind of filtration of CK, yeah, or different metrics. So that should be very interesting question, at least for students try to do understanding in analysis. And now I define the notion of Hausdorff measure. So that just recall that is the only recalling the concept of Hausdorff measure. So on any metric space, E is a distance D. Yeah. So diameter is a supremum of the distance between X and Y, and A alpha K is the volume of the ball of dimension K. No, zero, that's a center, but actually that I made remove 0 because the space homogeneous, so that depend on only radius. So I better to remove 0 here, that radius 1. And then the k-dimensional Hausdorff measure is defined as follow. HK is a limit when delta go to infinity. That means that how to say you want to cover S some subset by set of the diameter less than delta, right? S is like diameter lambda. And then I consider the kind of sum of the diameter in K. So the thing is a definition of the Hausdorff measure is a true thing. The cover some set by set of the small diameter delta, and looking at the sum of the diameter in the power K, yeah, divided to 2 normalization, and the let delta go to 0, then we have some number. And that is a proof that in classical book by Federer geometric measure theory, but I cannot remember that really Federer proved it or somebody proved it before, that HK is a regular Borel measure. Yeah. So the definition of k-dimensional Hausdorff measure extend to any non-negative real dimensional k by extending the definition. Alpha k is the following definition. So I change alpha k is here. Gamma is a gamma function, and then you know that's a kind of fractal measure, yeah, fractal subset, yeah, so it has a non-integer measure. So that's very interesting thing. You can look at the quite a good book by Morgan, geometric measure for beginner, and where he explained on the beautiful phenomenon. Yeah, so many things from the so how to say geometric measure theory from the pupil of Morgan and many pupil. That is a kind of analysis for singular space through measure theory. Yeah, so that's exactly good for working with a statistical model. But there are many things you can try to see, look at a lot of examples using this concept of geometric measure theory. But the problem that of course yes, if you can compute many things, and you or at least not compute, estimate many things, and you get, but estimation is also maybe hard thing. So that's that. Then what is no, that's if the k is bigger than dimension of h, then the Hausdorff measure of b is equal 0, and if k less than h dimension of h, then Hausdorff measure of h is infinity. So that we have the only non-trivial Hausdorff dimension in the only dimension Hausdorff dimension. Yeah. And what is the more interesting, that's they say that's if and G is Riemann manifold, Descartes this metric space is a Riemannian distance. You know that's a Riemann manifold is a Riemann metric space. Then the Hausdorff measure on M concise is standard volume defined by metric. Yes, that can be that is standard result. You can see in at least in our paper we have a citation. You can check for the proof. And now that's even more than that. You need some map is the only Lipschitz map from open domain. You can define something like a Jacobian of Lipschitz map, yeah. And that is the define almost everywhere. And then you can define the area formula, because the integration of the Jacobian is a Hausdorff measure. Yes, like a push map. Yeah, like a usually how you so that's you don't need smooth map to study how the map mapping between here's the only metric space, yeah, Riemann manifold, but that's why you need that area formulas, and you we have some theorems following. I shall tell you later. That maybe that's a it for your area formula is important for proving that Hausdorff measure on M coincide standard volume, because in classical books they consider first only for the case of M is the Euclidean space, but once you have the area formula, you can prove it for any Riemann manifold. Now I call that the Hausdorff measure on diffeological statistical model to integrable is a Hausdorff Jeffrey measure. Jeffrey measure because he first considered such kind of measure, but for the very regular space, one day, I mean that if he has a manifold, he didn't know on this theory, and here is a kind of generalization of his concept. Yeah. Now I just want to show that okay, only the thing is 9, but the Y generation is a natural. To prove that the generation is a natural, I need to use some kind of the categorical approach. And categorical approach for the probability theory and statistics was considered almost at the same time by Lauver in US and the Chensov in Moscow. Chensov write the short paper category of statistical mathematical statistics. Yeah, very bold paper because he was student of Kolmogorov, and Kolmogorov suggested him to consider geometric theory for probability theory and statistics. Yeah, but the one thing I only mentioned Lauver because Lauver has something more. If you look at the Chensov book, he didn't know how to make this very nice. Yeah, and then Lauver also proposed categorical approach to probability theory. So even you know things that you have to do category, but how to do it, that is also not obvious. Yeah, and then that have to say morphism, Markov, Kernan, Chensov also know it, but how to make the space of Px is the natural sigma algebra. So try to do everything is a measurable space. We consider categories and every object is a measurable space. Mapping the Markov kernel, yeah, and then how definition of this natural to measure a space. That means supply some sigma algebra on this space. Here's a kind of my a little bit modification of the original. I mean not modification, reformulation. So I define the space of simple function on the measurable space as simple function. You know that's a stepwise function on the constant on some measurable subset. Now I denote that I is mapping because that is I see it's nice because that is linear space. Yeah. So every time you have some extra structure, you have to try to use it. So now I consider the linear mapping from Fx to space of Hom of Sx to R. Yeah. So that is the only algebraic dual of the Banach space. So F to go to IF by taking integration. That means that for any simple function and I pairing is a probability not probability finite measure by integration of F over X du mu. And then I say that that is kind of my reformulation of Lauver, but many people may know, but they didn't write in this way. So sigma VW is the smallest sigma algebra on SX such as EF the measurement mapping, because in the category of the measurement space, you want everything is a measurable, right? So you ask that this map is a measurable. For on F is simple function, and then that is smallest sigma algebra. Yeah, so that we have some sigma algebra, and the map is that linear map is a measurable. And now mu is a space of on finite non-negative measure. Then you denote it any subset. You can restriction of the sigma algebra on Mx. Mu star is anything non-negative, and Px is a probability measure, is subset of the non-negative probability measure. So now definition, a probability morphism or an arrow from the measurement space X to Y is a measurement mapping T bar from the H to the space of the probability measure. Now you already every object in our space is a measuring space. So therefore, you can define the notion of measuring mapping. So that's it is a way to say that's usually people say that's a Markov Kernel. You write a lot of condition A, B, C. You have the A is a satisfy measure mapping, the continuous, blah 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 for each F. But you can write very shortly. Markov morphism between X Y is a measure is defined by measure mapping from X to space of probability measure on Y. And that is the idea of Lauvia. Chenso wants to do it, but not so nice. Yeah? You look at his book and appendix. And Giri proves that if you have can define the inclusion of the H to P's by attaching Dirac measure, and he proves that it's a measure in mapping, right? So that is very nice. Once you have the X to delta X measure mapping, you can define that any measure mapping K from X to Y assign the probability morphism I on K X to Y, because you first X to Y and go to Y to PY, right? As a composition, that means measure mapping from X to PY. So that's a probability. So you consider as every measure mapping is a probability mapping. Now I see that's a answer. My friend statistician, he says that very thing, because the people in statistic only consider everything random, not so nice. Actually, nothing is random in our own. Everything is a mapping, measure and mapping, but we have to consider higher space. And higher space here is a space on probability measure. Yeah, so I identify anything like a random, because nothing is a random. We only don't know them, so that our ignorance, yeah, so uncertainty about something. So better to avoid anything random. Now once you have the probability morphism from X to Y, you can make some functor S of T. Yeah, so try to do some categorical language. S to T mapping from X to XY, and define S following S to T acting on mu is a significant measure. B is some measured subset on Y in the integration of the integration over the mu. Now Tx is a measure on S on Y, therefore apply to B is some number and you take integration. Yeah, and that is how he defines associate functor from X to XY. You have the mapping from X to Y, and then because actually we are interested mostly on the case of the because the T of Px belong to Py, and mostly you are working with the thing, better to not to write the PT and the MT, so just write T as a ST, because that is simplify if you know what you mean, that you cannot confuse. Now given probability mapping from X to Y and CK diffeological space, statistical space, Px dx, I define that Tx dx equal T is a mapping from Px to Py, and actually you can consider that from Sx to Y, and that's smooth mapping. So T is star is smooth mapping between Px to Py, and then if it's a compose, it's a smooth mapping, you can take the push forward, right? And therefore I push forward diffeology from X to diffeology to Y. And there's a proposition. Yes,
Fun. Sorry,
yes.
just wanted to ask if you need, how much time you need to finish. So is it okay?
Yeah,
Like 10 minutes? Yeah.
Yeah,
Okay.
I should finish very soon. So
Okay,
only
really?
check in. Thank you. So that's a proportion. That's a composition. Let's say diffeological statistical model that means compatible. It's a natural inclusion map, and it's on mode to increment, then it's on mode to increment. Yeah. then that means that you have everything agree. It's our notion in natural. And then in our later paper, it's usually you say that it's also hold for equally differential statistical model. And now that are more interesting on the according to the Fisher metric, on the you take the push for us diffeology, you have the following monotonicity. G mu of the V on V is bigger or unequal. That's on the image after push forward, and equality if T is sufficient for P. So that is why they think that the Fisher metric is a information, because information when you apply on the probability mapping Markov Canal, you only lost information. That means you need to something is a monotone decreasing along the probability morphism, and that is considered as a information inequality, monotonicity, and equality is sufficient. What means sufficient? Example, one-to-one measuring mapping is sufficient for any piece probability morphism. And then now using such concept, we consider the example of Friedrich. He considers the smooth family of the probability measure in like that. In the is the following diffeology. C curve equals C1 curve if the log into L2C. Actually, the I for Friedrich is statistician, so he tried to rewrite something statistician know in terms of geometric approach. So that I say that's something statistician already know, but only not so coherent, yeah, like he tried to do for mathematics. But what Friedrich tried to prove that he makes some computation line and says that group of the measuring mapping is isometrically on this subset. But this is by this theorem, that is because equality is sufficient in particular measuring maps, and you get another proof, short proof, of course, because you already proved something before. So Friedrich reason. Now in just 3 minutes, I just say about application. The application that in static, yes, that's the most important. Why the Fisher try to do it? Important. You know that you want to estimate the probability measure based on observation. That is the main problem in statistics. Yeah. And then PHV is coordinate mapping. It try to see that how far from our map to the true map. Yeah, true map. That means that assuming C is a true probability distribution, and then you say that VL. I just want to say that in Eivind Schneider, they only consider mapping from vector space, and very inconvenient because of vector space and could take a linear structure. But actually, you have non-linear structure, so you have to compute the function var phi to var phi is a map from the px to v, some vector space, and then that is a much natural setting. And then in this way, then you can take the expectation of the how far from our estimation from the true value, and you got the grammar inequality. Many people say that grammar inequality in people in physics consider like a Heisenberg uncertainty principle, because that it says that you can never estimate the thing correctly because they are Fisher metric. Then it says that the lower bound for our estimated, assuming the estimator is unbiased. Of course, that is people say that maybe that's not so nice, but at least that's many physicists say that Heisenberg uncertainty principle. And then for machine learning, you can use the natural gradient flow to do machine learning. And the use the Hausdorff measure, you can define the natural prime measure in based on statistical model. And that is a most interesting thing now in statistics and machine learning, because yes, based on model, consider everything is uncertainty, has some distribution, but we how to say, encode our uncertainty in terms of not less in terms of prior measure. And then I cannot say more about the statistical physics, for example, give measure, but that is maybe that we can discuss later. But that's some open question. Open question is many geometry should be understand, for example, existence affine connection, Levy connection, on tangent cone deflection, statistical model. And I talked to Patrick Iglesias Semur. He says that's and that of course that question had not been even treated in the China diffeological spaces, but different logical statistical model is natural subset of Banach space, so that we have more trick to do it. And theory of equally diffeological statistical model is also not yet well understood. And the concept of CK diffeological space is also not yet well understood. I mean, that's if K equal infinity, then okay. But if K is not infinity, not. Okay. And the many nations statistical are not too incredible and should consider Finsler metric instead of Fisher-Rao metric. And yes, application facility give measure in machine learning, and then there are two paper I report on, and thank you for your attention.
So thank you, Yvonne, very much. Let's thank her for a very nice talk. Okay. Are there any questions? So if you have questions, please just unmute yourself and ask. So maybe I'll ask a question. So if I understand correctly,
Yes.
so one advantage, well, certainly one advantage of diffeological spaces is that you can do differential calculus on spaces that are not smooth in the usual sense. They have conical singularities or something
Yes,
like
yes,
that.
right.
So how often do such spaces arise in statistical applications or in
Oh,
probability?
that is a lot of the application. I in my paper, it's I forgot to write the archive here, but once you click the, I already wrote in the abstract. Yeah, I forgot to write the number of so it considers I know that's many people on the day it considers that's very natural. Let me check my um, natural the example of statistical model using in the statistics. They have the singularity, and that's one of the pioneer on this field, that Amari. He tried to consider like a resolution of singularity, and the one guy, Japanese guy, he wrote the book, the algebraic geometry machine learning, because he tried to use on the statistical model is a algebraic singular space, and he used a kind of Hironaka resolution of singularity. Yeah.
But can you give a simple example where this
yes,
happens?
example. Just wait a moment, because I have to check the even example here. I just try to look at my example here. Yeah. Yes. Better if you like, I send show my paper. I'll write on the blackboard. So or maybe I talk here. So that I have here. That is if you look at my paper, it's Tushilin. Then it's on the page 7. I mean that first version, because you should put the second version soon. So that is they say that's how to say, the Gaussian mixture model from Watanabe, and also consider time model, Nin River model, or Arma model time series in the book by Amari. And it has singularity, and actually of this singularity it has a different compatible diffeology. I mean, I have the conjecture. I have not yet talked to Patrick Iglesias. That means that if you the manifold is a smooth mapping, smooth one-to-one, then you don't have you have the only one canonical, how to say, compatible diffeology, but you have singularity, and that you can have the different competition, such diffeology. Yeah, but that can be also very good problem for some student or even a good paper if you can develop the theory of the things. That's a many things in diffeological space they have not yet considered. Yeah, there's still a lot of paper, and Patrick is still very keen to have somebody to work on. Yeah. Okay, and then they use something like a blow up, yeah, because everything is nice. It's algebraical using there's a singularity, and they work on covering space. So that is a Japanese school, yes, Hironaka from Japan. They try to do a lot. So you look at our paper, the second paper, and actually yes, and I consider that even how to have the different diffeology using, because the singularity on singularity is on the tangent cone is zero. You don't have any tangent non-trivial tangent vector. In second diffeology, it has a tangent at least a non-trivial tangent vector, and therefore the two diffeology, they are not the same.
And so I noticed that in your talk, the one place where derivatives are really used is in this definition of the metric,
Yes.
right? Imitating the metric of a
Yeah.
Riemannian
And
manifold
yes.
on this probability
Yes. Yes.
model space.
Yes. That,
So if I understand correctly, this px on which you're trying to define the distance,
yes.
yeah, even higher, I think.
Diffeological distance here, yeah.
Yeah. So px, it's
Yeah.
sitting inside what you called sx,
Yes.
this which is a Banach space, right? So it
Space.
has a measure.
Yes.
Sorry, it
Yes.
has a metric and so on, and
Banach space, they
it's a
don't
metric
have
space.
metric. The Banach space is that's a very, how to say, Banach space is very complicated of the finite measure. But at every C, yeah. So the thing is the very subtle, because the first thing that everything linear know they have very different tangent space. Every point here's a measure, and tangent space of the that point only on the not tangent space consider in the class of the non-negative measures written very carefully in our book Information Geometry is a set of the N1 function of the let me show that I only erase. Yeah.
Okay, but so my question was, I think people probably thought a lot about defining an intrinsic metric on subsets of a metric space. I mean, the obvious way is to just restrict the ambient metric, but using curves has the advantage that it uses only the intrinsic distance on
No,
the subspace.
but next the space of on finite measure is not metric space, not Hilbert space. That's a Banach space, not Hilbert. They don't have metric. That means
No,
how
no, well, sorry, metric as in like metric space, like distance between points.
distance. That is yes, that total variation norm. That also
Yeah.
very yeah. So I
Yeah.
mentioned at total variation norm. So that is kind of Finsler metric. So nobody try to consider it on the Amari consider. But Amari consider not that I only mentioned as that part, and there also chance of he says that the total variation norm. Yes, that is exactly because the Banach space that's that is and then you have the different relation between total variation norm and the Fisher metric. Yeah, that is also noted by many people. Consider that what is a natural. And then, but as girls say, why you take quadratic form? This is very convenient. Yeah, linear form is a much more convenient. And then, if when I look at the theory of the Fisher metrics, they say that what is a canonical measure, Hausdorff measure is a good or not? Yeah, and then I also see some people who doesn't know anything about Hausdorff measure. He tried to do something like I guess, but I mean that I don't have time to check on this thing and do anything. So if somebody interested in, I have pleasure to turn on the question and relation. That statistics, no, but not yet. I think that's you can explain.
My question was a bit more general, so I was just wondering if there is any particular advantage to trying to use differentiability to define this intrinsic metric to on PX. Because I can imagine that you can consider forget about differentiability and just think of I have a subset of metric space and try to define an intrinsic distance on the subset by considering paths that only go.
I understand think about that question, but I have no time. But the only problem because I call that is the Hausdorff Jeffrey, because Jeffrey define for Riemannian manifold finite dimensional. So he defines such a measure. And of course, there are also many, that time they consider, that's invariant because that all depend on parameterization, something like that, yeah? So he know only elementary Riemann geometry. And everything should be finite dimensional Riemann submanifold. So I just say that how to define some concept that natural extends what also very famous.
Okay, so basically you extended something that was already worked out in a
nobody
smooth case.
did it. Even the kind of the very natural, you have the distance I, you do not define the Hausdorff measure. Nobody defines, people didn't know what is the geometric measure theory. Yeah, so there are a lot of things we can try to do.
Are there any more questions? So if not, let's thank Van again.
Okay, thank you.
Okay, so I'll stop recording now.